Welcome to the Retrieval-Augmented Generation for Beginners course by Simplilearn. So in this course, we will understand initially the introduction to RAG, and then we will get into the components of RAG, and after that, we will dive deep into the data loading as well as text splitting, and then we will see storing the chunks in vector stores and embeddings, and then we will see how to retrieve the data. The most importantly, we will build a multi-document agent, and finally, we will conclude the course. So let us begin with the first chapter, that is Introduction to Retrieval-Augmented Generation. So let us begin with the first chapter, that is the Introduction to Retrieval-Augmented Generation. So imagine you are chatting with an AI and you ask it a question. Who won the FIFA World Cup in 2022? The AI can't just guess. It needs real information. But most language models like the ChatGPT are only trained up to a certain point in time. So if something happened after their training, they wouldn't know about it. Then their RAG comes. The short for Retrieval-Augmented Generation solves this problem. So let us now understand what is RAG. RAG is like giving your AI a powerful search engine buddy. So instead of depending only on what it remembers from its training, it also retrieves the latest and the most relevant information from a connected source, like a document, knowledge base, or even the web, and then uses the information to generate a better response. So, RAG is equal to retrieval, that is find information, plus generation, that is writing answers. Think of it as a student taking an open book test. First, they look up the question and then they explain it in their own words. So, the question arises, why does it even matter? So, here's the thing. Most traditional language models have a knowledge cutoff. That means they don't know anything that happened after a specific date. So, RAG helps fix these problems. It improves accuracy by pooling the real information when needed. Then it provides the up-to-date responses, even if the AI was trained years ago. Then it reduces hallucination because it uses facts instead of making educated guesses. Then it makes AI more trustworthy in the critical tasks like the legal, healthcare, or even enterprise search. Now let us move and see what are its use cases. So RAG is super useful in many real-world situations, especially when accuracy and up-to-date knowledge are important. So here are a few examples. The first example we have is customer support bots. They can pull answers from the help docs, facts, or internal knowledge bases to give the relevant and the accurate responses. Then we have enterprise search. So employees can ask questions and get answers from the company documents, manuals, or the HR policies. Then we have healthcare. Doctors can ask about treatment guidelines, and RAG pulls information from the recent medical research papers. Then we have legal. The law firms can use RAG to find and summarize the case laws from a massive legal document repository. Then we have education. And students can ask questions and then AI finds the best answer from the textbooks or notes. So now let's move on and see how does RAG work. So let's break it down into the simple steps. The first step is the user asks a question. Then you type something like, what are the side effects of aspirin? And then step 2 is retrieve. So instead of only relying on its memory, the AI first searches a connected database like medical documents, articles, or PDFs. So this is done using something called a retriever model like the BM25 or dense vector search. Then we have the third step as augment. The most relevant documents or snippets are selected and combined with your question. And then we have our fourth step, that is generate. Now the language model like the GPT or the BERT takes this context and generates a final answer based on the real information it just retrieved. It's like asking a librarian a question and that is compared with AI. The librarian doesn't just answer from the memory. They first find the right book, that is the retriever here, and then read the right page, that is the augmentation, and then explain the answer to you in simple language, and that is generation. Then let's move on to the next chapter and see the core components of RAG pipeline. In this chapter, we will understand about the core components of the RAG pipeline. So to understand how Retrieval-Augmented Generation works, we first need to meet its core building blocks. The RAG pipeline is not a single model. It's a smart system made up of multiple documents, each playing a unique role. So here's a quick overview of the 6 major components. So what are the components of the RAG pipeline? The first component we have is query encoder. Then we have retriever. The third one is the knowledge base, also known as the document store. Then we have the re-ranker. The fifth one is the generator, that is the language model. And then finally we have the last one as feedback logo. Now let's break down each one to see what it does and how it helps the RAG system. The first we have query encoder. So what it does? The query encoder takes the user's question like what are the benefits of green tea, and it turns into a mathematical formula called a vector. So this makes the question searchable by the machines. Now, how it helps RAG? So without encoding, the system can't compare your question to the information in the knowledge base. The encoder makes sure that your query is in a format the retriever can understand and match with the relevant content. Then let's move on to the second one. We have retriever. So what it does? The retriever uses the encoded query to search through the knowledge base and fetch the top matching documents or passages. So how it helps the RAG? This is where the RAG starts becoming powerful. So instead of relying on the model's memory, it now brings in fresh, real-world data from the trusted sources. Now, this also boosts the accuracy and reduces hallucinations. Then let's move on to the third one. We have knowledge base, that is a document store. So the knowledge base is the library that holds all your searchable content, like the PDFs, support documents, manuals, research papers, and etc. So how it helps RAG? This is where the truth lives. A well-structured, regularly updated knowledge base ensures your AI assistant can retrieve the current and reliable information. Then let's move on to the fourth one. We have re-rank. So after the retriever pulls the top end documents, the re-ranker re-evaluates and reorders them based on the relevance to the question. Then how it helps RAG? So sometimes the retriever brings okay results, but not in the best order. So the re-ranker acts as a quality checker, pushing the most useful documents to the top before the generator even sees them. Now let's move on to the next one. We have generator, that is the language model. So this is your AI's voice. The generator, like the GPT, takes the question plus top documents and crafts a human-like informative answer. So this is where the magic happens. Instead of guessing based on training data, the model now uses retrieved facts to generate the grounded, accurate responses. Now moving on to the sixth one, we have feedback loop. So the feedback loop collects user reactions like the upvotes, downvotes, or clicks and feeds that back into the system. So the feedback loop collects user actions like upvotes, downvotes, or clicks and feeds that back into the system. So how it helps RAG? So this loop helps the RAG system learn over time. So if users consistently like certain responses or sources, the system adjusts to prioritize them next time. It also helps to retain or fine-tune the retriever and re-ranker. Now let's move on to the next and see the results. In this chapter, we will learn about the document loading and splitting. So in order to create an application where you can have a conversation with your data, you first have to load your data into a format where it can be worked with. That's when LangChain document loaders come into play. We have over 80 different types of document loaders, and in this lesson, we will cover a few to get comfortable with the concept in general. So let's jump in. So Let's understand what are loaders. So loaders deal with the specifics of accessing and converting data from a variety of different formats and sources into the standardized format. There can be various places where we can load our data from, like the websites, databases, and YouTube, and many more. And these documents become converted into the data types like PDFs, HTML, JSON, Word, PowerPoint, and more. And so the purpose of different data loaders is to take this variety of data sources and load them into a standard document object, which consists of the content and then associated metadata. So there are various types of document loaders in LangChain. It's not possible to cover them all, but here we have a rough. The first one is public unstructured. So the data that is freely available to everyone, but doesn't have a fixed format. For example, the social media posts, blogs, articles, and YouTube videos. Then we have public structured. So here, the freely accessible data that is organized in a clear format. For example, the government census data, stock market data, weather reports, and more. Then we have proprietary unstructured data. That is the private data owned by the companies, but it's unorganized. For example, the customer service mails, internal company reports, recorded phone calls. And then we have this proprietary structured, so the private, well-organized data owned by the companies. A bank's customer transaction records, there is a Netflix user watch history, Amazon sales database, and more. So let's now jump into the fun part where we actually see how actually using document loaders work. So regarding the OpenAI API pricing, you can go directly to this openai.com API pricing wala website, and then when you scroll down, you will see and explore the detailed pricing, and you go there and you will basically find all the latest models with the input, the cached input, and the output as well. So in this course, we are using the GPT 3.5 Turbo, and its input is $3 and the training is $8. And if you contact the pricing, you will see it cost $0.5 and the output is $1.50. You can basically take up any API that suits well in your project. So initially, we are going to import some environment variables that we need, like the OpenAPI key. The first type of documents we're going to use would be PDFs. So let's see this. So we have downloaded the relevant document loader from the LangChain, and we're going to use the PyPDF loader. We have loaded a bunch of PDFs into the documents folder in the workspace. And so let's choose one and put it in the folder. So let's load the document just by calling the load method, and we will run this. Now let's take a look on the length of the pages we have downloaded, and we can see that we have 22 different pages in the PDF. So each one is a unique one. So let's look at the first one. So let's run this. So let's see the first content of the page. You can see the instructor is Andrew. Okay, good morning. Welcome to CS2229, the machine learning class. So this is the first page. So now here you will basically get a piece of information. That is the metadata, and we'll run this. And basically we can see there are two parts, the source. So till that .pdf, basically it is the name of the file we have loaded it from. The other is a page field, and it corresponds to the page of the PDF. So the next type of document we are going to look is at the YouTube content. There's a lot of fun content in YouTube. So a lot of people use document loader to ask questions about the content, lectures, or anything like that. So let's see. So here we have imported certain things. The key parts are YouTube audio loader, which loads an audio file from a YouTube video. The other key part is OpenAI Whisper Parser. This will use the OpenAI's Whisper model, a speech-to-text model that converts the YouTube audio to text format that we can work with. So after the output, we can now specify the URL. So let's see that. So we can now specify the URL, specify a directory in which we save the audio files, and then create a generic loader as a combination of this YouTube audio loader combined with the OpenAI Whisper Parser. And then we can load the documents by calling the loader.load corresponding to YouTube. Take a few minutes to load. So after this, we'll see the next. You can now see that it has generated the first output, and after that we can actually take a look on the page content, and this is the first part of the transcript from the YouTube video. You can see this. So the next set of documents we are gonna go with is how to load the URLs from the internet. So there is a bunch of educational content on the internet, and it will be pretty cool to actually just chat with it. So we are going to enable that by importing the web-based loader from the LangChain. And here basically we can choose any URL, and here I have chosen one markdown file from the GitHub page and created a folder. So let's then call the loader class. So we have called the loader class. Then we can even just take a look at the content, and we can see a lot of blank space over here. And when I scroll down, then you can see some content over here, and then again blank, and then again content. And this is pretty interesting. So finally we will cover how we can load data from the Notion. You have to follow certain steps from the Notion side to duplicate the page into your own Notion space and export them as markdown or CSV file. Then unzip it and save it as a folder that contains the markdown file for the Notion page. So then here we have a specific format, and we can use the Notion directory loader to load the data and get documents that we can work with. Now let's take a look at the first page of the content. And you can see this is a living document with everything we have learned working with people while running a startup. And of course we continue to learn, therefore it's a document that. So it's basically the part. We can clearly see that it is a markdown handbook, that is a Blendis employee handbook. And I'm aware that a lot of people has worked with Notion and has a Notion's database. So it's a great opportunity to export that data and bring it here and start working with this. And then finally we see the metadata over here, Blendis employee handbook. So now after we have loaded the data successfully, we will now get into and see the splitting of the data. So here we just went over on how to load the documents into a standard format. Now we are going to talk about how to split them up in a standard format. So it may sound easy, but there are a lot of subtitles over here. So document splitting happens after you have loaded your data into the document format, but before it goes into the vector store, and this may appear really simple. You can basically skip the chunks according to the length of each character or something like that. For example, we have a sentence that the Honda Accord boasts an impressive 192 HP engine paired with a seamless 10-speed automatic transmission, delivering a smooth yet powerful ride that will leave a lasting impression. So we can split this document into two chunks. So the chunk 1 would be the Honda boosts, and then the chunk 2 will be the rest part. An impressive 192 HP engine paired with a seamless 10-speed automatic transmission, delivering a smooth yet powerful ride that will leave a lasting impression. And we are trying to answer one question, that is, what are the specifications of Honda? But here is the tricky part. None of the chunk alone can answer the question. So how you split one information, that is very important to get the relevant chunks of information. So the basis of the all text splitters in LangChain involves splitting chunks in some chunk size with some chunk overlap also. So there are various types of splitters in LangChain. So the first one, we have the character text splitter. So it basically splits the text based on a specific character. For example, /n with a chunk size and overlap. And then we have markdown header text splitter. It splits markdown documents while preserving the headers and structures. And then we have the token text splitter. That is, it splits the text based on the token count, ensuring the compatibility with LLMs like GPT. And then we have the sentence transformers token text splitter. And it uses the sentence transformers to split the text intelligently based on the semantic meaning. And then we have recursive character text splitter, and it splits text hierarchically, first by large units and then by the smaller ones, that is the sentences and the words. Then we have language, that is used for the language aware text splitting based on the linguistic rules. And then we have NLTK text splitter. It utilizes the NLTK to split the text into meaningful sentence-based chunks. And then we have the Spacy text splitter. It uses the Spacy's NLP models to split the text while preserving the grammatical structure. Now let's see how to split the documents for real. So from here, we have imported OS, OpenAI and systems, and then from the .env, we have imported the load.env and the find.env, and we have set up our OpenAPI key. And then we have imported the recursive character text splitter and the character text splitter from the LangChain text splitter. So we will run this. And over here, we are mentioning the chunk size to be 26 and the chunk overlap to be 4 beforehand. And over here, we are initializing the art splitter with the recursive character text splitter, and we are initializing the chunk size and the chunk overlap. Then we are again initializing the C splitter as the character text splitter, and chunk size to be the chunk size, and chunk overlap we have done before also. So we will run this, and here we have the first text and we will pass this. Then we have this R splitter for splitting this text one. So we'll see this. So you can basically see there is no difference. So for this, we have a different example, and we will pass this and now we will see the result. And now you can see basically it has splitted the text, but the fact is we have a chunk overlap of 4, but it looks like 3. So let's see more examples. We are again passing this text number 3, and we will text split it with the use of art splitter, and you can basically see it has created ABCDEFGHIJKLM LMNOPQRSTUVWX, the WXYZ. Now let's apply the C splitter on the same example, and you can basically see it has again joined the whole text. This is nice. So here then the C splitter, we are adding a separator to be as the inverted commas. So we can see we have already got the result before, but here it is just separated with the inverted commas for more understanding. Here now it is the best time to actually pause and try out your own examples like this. But then we have a different example, and this time we have a paragraph. And let's now see the length of the text. It's 496 words. So we will now see the C splitter and the R splitter once again, and we will initialize it. This time we have the chunk size is equal to 450, and chunk overlap we don't have any, and we have a separator for the C splitter as the inverted commas. And in the R splitter we have chunk size as the same, no overlaps, and the separator should be a new line, 2 new lines, or a new line, or a double inverted commas, and everything. So let's just pass this. Now it's time to actually apply the C splitter over the some text we have generated. So you can basically see it is separated with the inverted commas. And here now in the R splitter, we will then apply it over the same text, and you can basically see the double inverted commas. So here what we have done is we have reduced the chunk size, and we have added period to the separators. So let's now see. Now you can basically see the difference. And let's Now see, we have made a difference of, we have added this operators. And let's now see the difference. We have now loaded one PDF from the machine learning lecture 1 and we have called the loader class from pages. So here we are importing the character text splitter from the LangChain text splitter and we have a separator of /n and then we have a chunk size of 1000 and chunk overlap of 150. So let's run this and then we can basically call the text splitter.split documents pages and we will run this. Let's now see the length of the document, that is 77. And then we have a length of the pages, that is 22. And now we are importing the Notion directory loader. And then we are passing one Notion database and then we'll load this. And then we are using this text splitter in the Notion database. And let's see the Notion DB length. And you can see it is 52. And then basically you can see the length of the documents and then we'll see it is 353. Now basically we can actually split on the basis of token count explicitly only if we want. So let's now see that. So we are importing the token text splitter from the LangChain. Here now we are actually keeping the chunk size to be 1 and the chunk overlap to be 0 and we are passing it under the token text splitter. So here we again came with a one text and it doesn't make any sense but it's okay. And then we are going to pass this text 1 through this text splitter.split and we'll run this. And then you can basically see it has splitted the whole text and it has also separated with the inverted commas. And then we are applying this to the pages and let's now see the first document. And then you can basically see it is filled with page content, metadata that is containing the source, the lectures, the page we have. This is basically the field as I have already discussed. And then let's move on. And lastly, for the token-wise splitting, let's see the metadata of the page. And you can see it is the machine learning lecture 1 PDF, page and fidelity. Now let's see the context-aware splitting. So here we have imported the Notion directory loader and we have imported the markdown header text splitter. So here we have one markdown document and let's run this. And then basically we have these headers to split. That is first hash and then we have header 1, double hash we have header 2 and triple hash we have header 3. And here now we have this markdown splitter. And we can basically see we have MD header splits equal to markdown splitter dot split text markdown documents. And then now let's see the MD header splits 0 that refers to the first document. And now you can basically see, hi, this is Jim, this is Joe, metadata header, title, header 2, chapter 1. And let's now see the second one we have. And this is Lance. Chapter 1, Header 3 section. Let's now see this on the new Notion database. Here basically we have this headers to split, header 1 and header 2. Then similarly we have this markdown header text splitter and we are using those headers to split on headers to split on. This is basically we are initializing it. So let's run this. And let's now pass this first text and a markdown splitter split text. And let's see. And let's now see the first document. And this is basically what we can see. Now guys, let's move on to the next chapter. So in this chapter, we will talk about the storing, the chunks and vector stores and embeddings. So imagine you are reading a 200-page book and you want to remember the most important ideas. So instead of just memorizing every word, you highlight the key sentences and write them on the sticky notes. So these sticky notes are your chunks. So in the world of AI and large language models, especially in the Retrieval-Augmented Generation systems, we do something similar. We split the large documents into the small meaningful chunks or text. So this helps the model retrieve only the parts it needs to instead of reading the whole thing again and again. Now let us see why storing in chunks is important. So you might ask, why can't we just store the full document? And that is a valid question. So LLMs can only process a limited amount of text at a time. So giving them a whole book can overwhelm them or cause important parts to be ignored. And so storing information in the smaller chunks makes it easier for the model to find the relevant content quickly. And then the smaller chunks improve accuracy by helping the model focus on the specific details instead of giving vague answers. So let us now see what are embeddings. So now here's the cool part. How do we find the right chunk later? That's where embeddings come in. So embeddings are like the turning words into numbers that capture meaning. Think of them as GPS coordinates for ideas. For example, the words dog and puppy might be close together in the embedding space because they have similar meanings. So let's say we have a chunk. Python is a programming language used for the data science. So we convert this into a list of numbers or embedding like 0.12, 0.98, minus 0.34 and more. So this vector represents the meaning of that sentence, but not in words. So now let's move on and see what are vector stores. So we have turned our chunks into embeddings, but where do we keep all these meaning vectors? In a vector store. So think of a vector store as a smart library. So instead of organizing books by titles, it organizes chunks by meaning. So when you ask a question, it compares your query's embedding with all the stored embeddings and pulls out the most relevant chunks. For example, you ask, what is Python used for? The system converts your question into an embedding and searches the vector store for the closest match, which might be the chunk we saved earlier. So the answer is Python is a programming language used for data science, and boom, that's your answer. Let's now see how are they helping together or why storing in chunks is so important. So putting it all together, you split the document into chunks. Then you generate embeddings for those chunks as well. And then you store the embeddings in a vector store. So when a question comes in, you generate its embedding. The vector store finds the most relevant chunks. And finally, the LLM uses those chunks to generate an accurate response. So this is how the RAG system works. They're not just smart, they're efficient. They don't try to memorize everything. Instead, they store what matters in the right format and retrieve it when needed. So let's now see everything in action. So to start, we will once again set the appropriate environment variables. So here we have already discussed how to load a document and how to split them just now. So now here we will be working on with the same set of documents. So let's run this. So here now, after loading the PDF and all the documents, we are now planning to split them. So here basically we are importing the recursive character text splitter. So text splitter is equal to recursive character text splitter. We are initializing the text splitter. Then we have mentioned the chunk size as 1500 and chunk overlap equal to 150. So let's run this. So once again, if I have missed a point in the loading PDF, so there are a set of CS229 lectures, and if you look closely, you will see we have duplicated the lecture 1 2 times because of simulating dirty data. So that we can now see that we will initialize this text splitter. Now we can say this, we have created more than 200 chunks, 209. Now time to move on to the embeddings. Let's take our splits and embed them. We will use the OpenAI to create these embeddings. So we'll run this. Now, before trying with the real world examples, let's try out some other examples too. So we are planning to pass these 3 sentences over here. Sentence 1 is, I like dogs. Sentence 2 is, I like canines. Sentence 3 is, the weather is ugly outside. So we'll pass this. And now here, we can actually see that we have created 3 embeddings for 3 respective classes for the 3 sentences we have. So we'll run this. So we can now create an embedding class for each sentence. So we can import the NumPy to import them. We'll expect the first 2 sentences will be very similar. So we'll check that. And now we will be using this dot product to compare them. So the dot product in here multiplies the corresponding elements of the two vectors and then adds them up, giving a single number. It helps measure similarity between embeddings. Higher value means more similarity and lower value means less similarity. So we will run this. Now basically you can see that the dot product of the first and the second was quite higher respect to the first sentence and the third. So we can get a significant lower value. So now let's read the dot product between 2 and 3. And if you run this, we can see that it's almost the same. Now I will suggest you to pause the video and try out a few different examples and their dot products. So let's move on to the real world examples. It's time to create embeddings for all the chunks of the PDFs and store them in a vector store. So the vector store we will use here is Chroma. So let's import that first. So here we are importing Chroma database and we are importing Chroma from the LangChain vector stores. And before we run this, LangChain has integration with lots of vector stores. We are using Chroma here because it's lightweight and in memory, which makes it very easy to get up and start with. There are other vector stores that offer the hosted solutions which can be useful when you are trying to persist large documents of data or persist it in the cloud, store it somewhere. So then we are going to save this in the vector store so that we can use it for the future lessons. So let's create a variable called persist directory which we will use later on at docs/chroma. So here let's also make sure that nothing is there already. So here basically we have created the vector store. So we'll call the Chroma from documents, then passing on the splits that we created earlier. So passing through embeddings, now this is the OpenAI embedding, and finally passing through a directory. And the directory is persist directory that we have created to store for the future use. So we will run this. Now we will take a look at the collection count. We can see that this is the same as that of the split that we did previously. So let's now start using it. Think of a question that we can ask. We know that this is a class lecture, so we can ask. So if there's any email address we can ask for regarding the class or anything. So the question we're gonna pass over here is there any email I can ask for help? So we are going to use the similarity search method over here, passing the question, and even k is equal to 3, which specifies the number of the documents that we want to return. So we will run this. And let's then check the length of the docs. Now that we will see the length and it's 3 as we have specified. Now let's take a look at the content of the first document. It's in fact about an email address and is obviously an email we can send queries to. So now you can see that there is an email. This goes to the accounts that's read by all the TAs and me. So this is nice. So after doing this, let's be sure to persist the database for future use. So we'll persist it. So basically similarity search will give you 80% of the great results. But there are some edge cases. And now we are gonna discuss that only. Now let's ask a question. What did they say about the MATLAB? And we'll pass this. And we are trying that similarity search over here. And we'll passing the k is equal to 5. Now let's see the first document. And then we'll look at the second one. And notice that we are getting duplicate chunks. So because of the duplicate machine learning lecture 1 PDF in the index, semantic search fetches all the similar documents, but does not enforce diversity. So docs 0 and docs 1 are identical. We can see a new ferial mode now. Let's pass one question. What did they say about the regression in the third lecture? So we'll pass this. We can check this because we have information about metadata about what lectures they came from. So we are using the similarity search, passing through this vector db, and we are keeping the case values equal to 5. So let's loop over this document and print the metadata. So we can see a combination of results, some from the lecture 3 and some from 2 and 1. The reason it is failing is that the third lecture and the fact that we want documents from the third lecture is a piece of structured information, but we are doing a semantic lookup based on the embeddings, where it creates an embedding for the whole sentence and is probably a bit more focused on the regression. So let's now look at the fifth document, the one that comes from the first lecture. It does refer to the regression. So if it is picking up on that but not on the fact that it's supposed to be querying documents only related to the third document, because again it is a piece of structured document. So it is a good time to pause and truly figuring out some more questions and try changing the value of k. So in this lecture we have seen the basics of semantic search and also the failure modes. Let's move forward in the next part and try to address those failures and retrieval too. In this lesson, we will dive deep into the retrieval and few more advanced methods for overcoming the edge cases. So let us understand what is retrieval in RAG. So in RAG, retrieval refers to fetching the relevant documents or data from a knowledge base like a vector database, or the local files to answer the user queries. It helps in searching, filtering, and retrieving information efficiently. Now, let us move and see where retrieval is used. So, it is used in the chatbots with memory. For example, retrieving the past conversations. Then we have question answering system. That is, for example, retrieving the FAQ answers. Then it can be used in the AI-powered search engines. That is, for the semantic search. So, the techniques we will be talking about today are new to the market. The first one we will be talking about is maximum marginal relevance. That is, the MMR is a smart way to select the diverse and the relevant information from a large set of documents. So instead of just picking the most similar results, it balances the relevance and diversity, ensuring that the retrieved results are not too repetitive. So MMR is used in the Retrieval-Augmented Generation, that is the RAG, to improve the search results by selecting both the relevant and the diverse documents. So imagine searching for the best AI tools. So without MMR, you get the 5 results about ChatGPT, too similar. But with MMR, you get the results about ChatGPT, Gemini, Claude, Midjourney, and Copilot. So let's now move on to the second one we will be talking about is LLM-aided retrieval. LLM-aided retrieval is a smart way to improve the search results by using a large language model to refine or guide the retrieval process. So instead of just fetching documents based on the keyword similarity, the LLM helps in the better query understanding, ranking, and selecting the relevant information. For example, without LLM-aided retrieval, a search for the AI in marketing may retrieve random AI articles. So with LLM-aided retrieval, the LLM understands the intent and retrieves the specific articles on AI tools for marketing. So let's now move on and see the demo. So let's see all the techniques in action. So we will start with loading the environment variables as we always do, and then we'll run this. So let's then import Chroma from LangChain vectors. We will also import OpenAI embeddings, and we will also create this persist directory we have created before, the docs Chroma, and we will run this. We will now create embeddings. Embeddings equal to OpenAI embedding vector Chroma, and then pass this persist directory and embedding function. So we will run this. So now we'll try to print vector db dot collection dot count, and we'll run this. So after looking at the collection counts, we can see this is 209 documents that we loaded before. So let's now begin with maximum marginal relevance MMR. So we have all this text that got loaded and all are about mushrooms. So we'll create a small database equal to Chroma dot from text and we'll pass text, comma, embeddings equal to embedding. So this is type of a toy example and we will run this. So I have a different question. Tell me about all the white mushrooms with the large fruiting bodies. So I'll run this and we'll create plugin called this small db dot max marginal relevance search. We will pass the question, then k is equal to 2, comma, fetch. Make sure you give the correct code and we'll run this. So here, if you see, we have still k value as 2, but fetch k is equal to 3 to fetch all the 3 documents originally. So now let's go back to a question, a previous lesson where we asked about MATLAB. So the question is, what did I say about MATLAB? And we have the vector similarity search over here and the k value is 3. So now we'll basically compare docs ss 0 dot page content and we will run this, and we will again basically I'll copy this and I will change 2 to 1. Now we can actually see that both are the same. Now we will use MMR to actually find out the difference. So let's write docs MMR first document dot page content and we will copy this, paste it here and we'll make it as 1. Now the second one is different. It's getting some diversity in the environment. Let's now move on to the next part. We have a different question again and we'll try to run this. So we are here again using the vector DB similarity search, and if you see, it is the third lecture over here. So we'll try to run this. Now if you see this, that you will understand that it got retrieved, that is exactly like the initial. So now we are going to use self-query retriever. So I'm importing OpenAPI and self-query retriever and attribute info. Let's run this. So here again we are specifying the metadata attributes like the name, the description and the type, and if you see the difference, the page from the lecture and here in the description it is the lecture, the chunk is from should be one of the documents from this. So let's run this. We will now specify it more and use LLM as OpenAPI model, and we will give retriever as self-query retriever from LLM and vector DB and everything, and we will also here verbose is equal to true. So we will run this. So here we are basically retrieving the relevant documents and passing the question, and it is okay, and we'll print the metadata. This can be ignored and you can actually find out the metadata. So there are some additional tricks over here for compression. That is another approach for improving the quality of the retrieved documents is compression. So information most relevant to a query may be buried in a document with a lot of irrelevant text as well. So passing that full document through your application can lead to more expensive LLM calls and poorer responses. So contextual compression is meant to fix this. So I'll import contextual compression retriever and we'll run this. Here we are passing this pretty print documents through the documents, and we are even giving all the specifications of the double new line, page content and everything, and we will run this. So here we will wrap our vectors stored. So we'll run this. We can now create a compressor with the LLM chain extractor as well. So we'll run this. We can now create the contextual repression retriever and then the best retriever from the vector store. And now we are passing the question and we'll run this. Now we are passing the question. Seeing the output, you can find out that the documents are shorter than the normal one. And they have some repeated stuffs as well. So it's not worth nothing that VectorDB is not the only kind of tool to retrieve documents. The LangChain retriever abstraction includes other ways to retrieve documents such as TF, IDF or SVM. So let's see. We will begin with loading the environment variables like we always do, and we will run this, and then we will see loading the PDF, and then we are using the recursive character text splitter to split the text, and we are specifying the chunk size, the chunk overlap, and finally splitting it. So after splitting is done, we will be using the retrievers SVM retriever and TF IDF retriever, and we will run this. And then finally, we will ask this question, what are the major topics for this class? And we will basically run this. Now you can see the page content. Let me just check about what questions you have right now. So if there are no questions, I will just, it has given it. So now we are using the TF-IDF retriever and let's run this. So this is the right time to pause and try your own examples. And now down the line in the next lecture, we will see how we can ask questions and get the relevant answers. So in this lesson, we will learn how to extend the normal agent to handle multiple documents and increasing the degrees of complexity. So now, initially we'll begin with setting up the OpenAPI key. And secondly, we will import the Nest Ascencio. And then the first task is to set up our function calling agent over 3 papers. So we do this by combining the vector summary tools by each document into a list and passing it to the agent so that the agent actually has 6 tools in total. So here we have downloaded 3 papers from the Clear. So this includes the MetaGPT for the last time. And this also includes the long LoRa as well as the self-RAG. So next we will convert each paper into a tool. So this is basically a helper function. That is the gap doc tools, which automatically builds both a vector and index tool as well as a summary index tool over a given paper. And the vector tool performs the vector search and the summary tool performs the summarization of the entire document. So for each paper we are getting back both vector tools and the summary tools. So here we'll run this. So then we will define the 3.5 Turbo from the OpenAI as the large language model of our choice. And now, if we run this, it is basically the GPT 3.5 Turbo. So if we really take a quick look at the number of tools that are going to be passed to the agent, we will get 6. Because we have 3 papers and 2 tools for each paper, a factory and a summary tool. And the next step is to construct our overall agent worker. And it includes all the 6 tools as well as the large language model that we pass out. And we are able to ask questions across these 3 documents or within a single document. For now, let's ask a question. Tell me about the evaluation dataset used in the long LoRa and then tell me about the evaluation results. And we have got the answer that one of the evil datasets uses the feature of 19 test split. We are able to look at the evil results for our long-haul models. The next question is, give me a summary of both the self-RAG and the long LoRa. So this will basically allow us to do the summarization of the 2 papers. So first, we'll call the summary tool for the self-RAG with the inputs of its name. So we will run this. And you can basically see added user memory. You can basically see added user message to the memory. Then we have the calling function. Then we have the output. Then again we are calling function and then we have the output. And this code defines the tool list, the URLs and the papers. So the URLs list contains 11 links. to research papers in the PDF format from the Open Review website, while the papers list consists of the corresponding file names that likely represent the downloaded versions of these papers. So here each URL in the URLs list maps to a specific file name in the papers list, suggesting that these names might be used to save the downloaded files. So this setup can be useful for automating the downloading process, keeping track of the files, or referencing papers by their assigned names. So this code basically processes a list of the research papers by extracting the specific tools for each document using the getDocTools function. So it begins by importing the getDocTools from the utils module and path from the pathlib for handling the file names. An empty dictionary paper to tools dictionary is initialized to store the mapping of each paper to its respective tools. The code then iterates through the papers list, printing a message to indicate which paper is being processed. For each paper, it calls the getDocTools, passing the paper's file name and its file name without the .pdf function. So this function returns the two tools, that is the vector tool likely for converting the text into embeddings for the NLP task, and summary tool which might generate the summaries of the paper. So these tools are then stored in the dictionary with the paper file name as the key and the tools as the value. So this setup enables efficient document processing, allowing for easy access to vectorized representations and summaries for the research paper. Now basically you can see the output. So this code creates a list called the all tools that collects of the tools from the paper to tools dictionary for every paper in the papers list. So it uses a nested list comprehension, which means it goes through each paper in the papers, retrieves its associated tools, a list of the two tools stored in the paper to tools dictionary, and adds each tool to all the tools. So as a result, all the tools become a single list containing all the vector and the summary tools for every paper rather than keeping them grouped by paper. So this approach makes it easy to access and process all tools together instead of dealing with them paper by paper. So here this code creates an object-based index and retriever for the tools stored in all the tools using the vector stored index from the llama-index.core library. So the object index from the objects function takes all the tools and organizes them into a searchable index. So the index CLS is equal to vector stored index argument specifies that the indexing method should use a vector-based retrieval, meaning each tool will be converted into a vector representation for the efficient searching. So this setup allows the quick retrieval of the relevant tools based on the similarity searches, making it useful for the tasks like finding related tools based on the user queries. Now this code object retriever is equal to object index dot as retriever is creating a retriever object from the object index, which likely represents as index collection of data such as documents or embeddings. The asRetriever method converts this index into a retriever, following it to fetch the relevant results based on the similarity. The parameter similarity top k equal to 3 ensures that when a query is made, the retrieval will return the top 3 most similar results based on their relevance. So this is useful in applications like search engines, chatbots, or recommendation systems where retrieving the most relevant information is important. So here the code tools equal to object retriever is asking the retriever to find the relevant information related to the given query. The retriever searches through the index data and retrieves the most relevant results based on the similarity. Since object retriever was configured to return the top 3 similar matches, it will return up to the 3 pieces of relevant information. The retrieved results are then stored in the tools variable, which can be used for further processing, such as displaying the information to the user or using it in an AI model. So this process is commonly used in the AI-driven search systems, chatbots, and question answering application to fetch the relevant data efficiently. So here the core tools2.metadata is accessing the metadata of the third retrieved result from the tools list. Since the tool stores the results returned by the object retriever.retrieve, each item in the tool contains both the retrieved content and the additional metadata. So metadata typically includes the extra information such as the source, timestamp, author, document ID or other attributes, and that describe the retrieved data. So by using tools.metadata, you are specifically extracting the metadata of the third result, which can be useful for understanding whether the retrieved data came from the adding context to the results or not. So the given code over here is setting up an AI-powered agent that can answer questions based on the retrieved information from a collection of papers. So first it imports the function calling agent worker and the agent runner from the llama index code.agent. Then it creates an agent worker using the function calling agent worker, which takes the object retriever as the tool for retrieving the relevant information and LLM to process and generate responses. So the system prompt ensures that the agent always relies on the retrieved data instead of the prior knowledge. So finally, agent is equal to agent runner wraps the worker inside the agent runner, making it easier to manage and execute the agent's task. So this setup allows the agent to intelligently retrieve and generate answers based on the predefined knowledge base, making it useful for the research, document analysis, and question answering applications. So this code is making the AI agent answer a query about the evaluation dataset used in the MetaGPT and how it compares to the SWB bench. The query function sends this question to the agent, which then retrieves the relevant information using the object retriever and processes the response using the language model. The retrieved and the generated response is stored in the response variable. So finally, the print str response converts the response into a string and displays it. So this allows the AI agent to provide a well-structured answer based on the available documents, ensuring an informed comparison between the two datasets. So this last but not the least code AI agent analyze and compare the two research papers, Long Laura and the Loft Q. The query function sends a detailed question asking the agent to first analyze the approach used in each paper and then compare and contrast them. The agent retrieves relevant information using the object retriever and processes the response using the language model. So the generated response is stored in the response variable. Finally, the retrieved and the analyzed answer is stored in the response variable. This setup helps in extracting the insights from the research papers efficiently, making it useful for the academic research, technical analysis, and AI-driven summarization. Now you can see that it has generated the output. In the next lesson, let's conclude this whole course. So lastly and finally, we have a conclusion over here. And the conclusion basically focuses on the future of RAG. So as powerful as RAG is today, its future looks even more promising. So in the upcoming years, we can expect the smarter retrieval, that is the more accurate retrievers that consider the semantic nuances, user preferences and intent, not just keywords. Then we have multimodal RAG, that is integration of not just text but also images, audio and video into the retrieval and generation process. Then we can even expect the personalized agents, that is the systems that learn from the user feedback loops in real time, delivering more relevant and personalized answers. Then we can even expect the memory augmented RAG, that is incorporating the long-term memory into agents so they can retain the context across sessions. Then we can expect the low latency, that is scalable RAG, that is optimizations in storage and retrieval that allow the RAG to work seamlessly even at the massive scale and speed. So RAG is evolving fast, from powering search engines to enhancing the customer support, healthcare, finance and education. So as these systems become more fine-tuned and grounded in the accurate and the real-world knowledge, they will bridge the gap between the static data and dynamic, intelligent responses, paving the way for the next generation of AI. So guys, congratulations on completing the RAG for the Beginners course. You have now built a strong foundation in the Retrieval-Augmented Generation by learning what RAG is, why it matters, and how it powers the real-world applications. From understanding the core components like the query encoder, retriever, re-ranker, knowledge base, and generator to hands-on demos in the document loading, chunking, storing with embeddings and vector stores, and building a multi-document agent, you have gained the practical skills to apply RAG effectively. So as you move forward, continue experimenting with your datasets and refining your pipeline to unlock the full potential of RAG in creating the smarter, context-aware AI systems. Thank you for watching.
Staying ahead in your career requires continuous learning and upskilling. Whether you're a student aiming to learn today's top skills or a working professional looking to advance your career, we've got you covered. Explore our impressive catalog of certification programs in cutting-edge domains, including data science, cloud computing, cybersecurity, AI, machine learning, or digital marketing. Designed in collaboration with leading universities and top corporations, and delivered by industry experts, choose any of our programs and set yourself on the path to career success. Click the link in the description to know more.
Hi there, if you like this video, subscribe to the Simplilearn YouTube channel and click here to watch similar videos. To nerd up and get certified, click here.